Welcome. In this video series, we're going to look at the fundamental theorem of calculus, and there's actually two parts of that theorem, but it's called the fundamental theorem of calculus because it literally is fundamental to calculus, because it relates differentiation and integration. And so we're going to see both of those and then try and figure out, when do we use what parts, how do we use each part? And so we're going to dive right in with the second part. Yeah, I know we're going out of order, because we've actually seen the second part of the fundamental theorem of calculus previously under the name of the evaluation theorem. And so the evaluation theorem was just that if it is continuous, and it can be piecewise continuous on a closed interval, then we have that the definite integral, right, calculating the area under a function f between endpoints a and b, is just given by capital F of b minus capital F of a, where big F is any antiderivative of little f. Okay? And so again, just a reminder that this theorem, or this expression, right, this is not only communicating the area between A and B, right, in a succinct way, but we are able to know, or we know that this is also expressed as the limit of a Riemann sum. So we would send n to infinity, and then inside of here we would let I iterate from 1 to n of f of xi d or delta x, right? And so delta x was the width of the rectangle, and then the f was the height. So we're taking, the area of each of the rectangles, n of them, and then just passing n to infinity. So the number of rectangles gets larger and larger and larger, giving us a better and better estimate of the area. Okay, and so from this, right, we are aware of how to find the area from 2 to 7 under this curve. So it would just literally be, in terms of notation, it'd be integral from 2 to 7 of f of, let's see, notation is t dt. And so then we would calculate this by substituting everything in, t minus 2, t minus 5, dt. And so we need to find an antiderivative, and the best way to do that is to expand it out fully. So from 2 to 7, and then I get t squared minus 7t plus 10 dt. Okay, and the antiderivative that I would find would be t cubed over 3 minus 7 over 2t squared plus 10t, and then I would need to evaluate this whole thing from t is equal to 2 to 7. Okay, and if I do that with maybe the assistance of a calculator or just number crunching longhand, I would get 25 over 6. Okay, so same sort of story as the evaluation theorem, just under the more appropriate name of FTC, Fundamental Theorem of Calculus, which we abbreviate as FTC Part 2. Okay, and then I have a note here. There's a related group work, but I also wanted to outline the proof. Again, and I mean this as an outline, right? So we are not going to go into the full details. For the full details, I'm going to say, please see Google or your textbook. But the idea is that we consider the interval xi to xi plus 1, okay, where I is, so for I an element of a, b, that interval, okay. Then we know by the mean value theorem, so mean value theorem, the only condition is that we have continuity of the function, which we do by the hypothesis. So the MVT would give us that there exists, okay, and this is my fancy way of saying there exists, okay, so there exists some xi star such that, actually I'm going to say xi in this interval that I've chosen, xi to xi plus 1, such that big F prime of xi star is equal to f of xi minus big F, of xi plus 1 all over xi minus xi plus 1, which, and actually I could reverse these, it doesn't much matter. The signs would work out, so let's change this to xi plus 1 over x minus xi, and that whole denominator, that is just delta x. Okay? And so if I rearrange this, this would be f prime of xi star would be the same as little f of xi star times delta x is equal to big F of xi plus 1 minus f of xi. Oops, don't want to do that yet. Okay, and then what do we know? Well, if we remember the definition of the integral, right, we have that xi plus 1 delta x there. So now, if I scroll back down a little bit, this would be equivalent to the integral from a to b of f of x dx, as long as, and maybe let me write this a little bit different. Let me write this a little bit differently. So now, if we were to look at integral from a to b of f of x dx, okay, we know that this is limit as n goes to infinity of sum n is I is equal to 1 to n of f of x I star delta x. Actually, it's f of xi, but we can put an f of xi star. That's fine. And then this is equal to limit as n goes to infinity of the sum from I is equal to 1 to n, and we know from the MVT work that we just did that this would be f of xi plus 1 minus f of xi. Okay, and if we were to write this out, okay, this would begin at f of b minus, and then it'd be like f of b, let's see, b, well, it'd be like x, it'd be kind of hard to write out, but imagine it'd be like I minus 1, it doesn't even capture correctly. Well, let's just do x alpha, and then plus f of x alpha, and then minus f of x beta, plus f of x beta, right? These are all just all the endpoints of the intervals that we've divided it into, plus so on and so forth, and then minus eventually f of a. And the point is, all of these would cancel out, and I'd be left with f of b minus f of a. All right, so that's the outline of the proof. Again, skipping over some technicalities, but that just goes to show that, yes, the evaluation theorem is true. We skipped over the proof, and now we can call the evaluation theorem the fundamental theorem of calculus and use it just like we use the evaluation theorem.